Welcome to lecture 5. This is the last lecture of week 1. So, we will continue our discussion on review of linear algebra. In our previous lecture, we started our discussion on review of linear algebra and we talked about vectors. Today, we will talk about matrices. An M by n matrix A is the rectangular array of elements. So, the matrix A can also be represented as shown. So, if you have a rectangular array where you have m rows and n columns, we say this rectangular array of mn elements as M by n matrix. So, the dimension of the matrix is m by n. So, it can also be represented as this, where small a I j represents each element of the matrix. Usual notation is ith row jth column. So, A22 is the element in the second row, second column, A2n is the element in second row, nth column, so on and so forth. So, normally we will express matrix by this capital letter or also by small letter with subscript I j within square bracket. Now, we will talk about matrix operations. First, let us talk about matrix addition. Matrix addition is defined between two matrices when the dimensions of both are same. So, let us consider A is a matrix of dimension m by n. Let us consider another matrix B with same dimension m by n. So, then the sum A plus B will be the sum of the corresponding elements. So, the first element of the matrix, that is the sum of A and B, will be the A11, which is the first element of matrix A, first row, first column, and the same first row, first element of the matrix B. So, A11 plus B11 will be the first row, first column element of matrix C. Similarly, all other terms. In general, this can be expressed as if A is represented as A I j, B is represented as B I j, both have same dimensions, then the elements of C I j will be A I j plus B I j for I equal to 1 to m and j equal to 1 to n. Note that the dimensions of both A and B must be same. Scalar multiplication. If A equal to A I j denote m by n matrix and let C be any scalar, then CA matrix will be a matrix with the elements of A, but multiplied, each element multiplied by the scalar C, as you can see in this matrix. So, C is a scalar, A is A I j. So, C A will be C A I j. So, each element of A will be multiplied by the scalar C. Matrix multiplication. If the matrix A is M by n matrix and B is n by q matrix, then the product between A and B is defined. So, the product between two matrices will be defined when the column of first matrix is equal to the number of column in the first matrix will be equal to number of rows in the second matrix. So, M by n matrix and n by q matrix can be multiplied. So, the product of A and B will be M by q matrix, and the element C I j of the product matrix C can be computed as sigma k equal to 1 to n A I k B k j. So, let us take this example, matrix A, a two dimensional matrix A 1 1, A 1 2, A 2 1, A 2 2. Similarly, matrix B. So, A is 2 by 2 matrix, B is also 2 by 2 matrix. So, the multiplication is defined and the product matrix C will also be 2 by 2 matrix. So, what will be the elements of the matrix C? That will come from this formula C I j equal to A I k B k j, where k runs from 1 to n. Note here, I is the number of rows in the matrix A, j is the number of column in matrix B. So, if the matrix A has these elements and matrix B has these elements, so the product matrix A B can be found out by this multiplication. So, what you do is you take A 1 multiply with B 1 plus you take A 1 2, you multiply with B 2 1, that becomes the first element of the product matrix. So, A 1 1, B 1 1 plus A 1 2, B 2 1. So, that becomes 1 1 element of the product matrix A B. So, what will be the 1 2 element? That means the first row, second element. So, that will be you take this first row and consider the second column of B. So, A 1 1 plus B 1 2 plus A 1 2 into B 2 2. So, that becomes A 1 2 element of the product matrix. Similarly, A 2 1 will be obtained as this multiplied by this and A and the 2 element will be this multiplied by this. So, it will be this. So, this way you can perform matrix multiplication. Let us now define certain common matrices such as identity matrix, zero matrix, symmetric matrix, etc. An n by n matrix, an n by n identity matrix is a square matrix as shown, where all the elements in the principal diagonal are unity. So, the identity matrix n by n is a square matrix with n rows and n columns, and all the elements in the principal diagonal are unity, all other elements are 0. If we post multiply or pre multiply identity matrix with any matrix A, the product becomes same A. So, A multiplied by identity matrix I is A, identity matrix I multiplied by any matrix A equal to A. Of course, the matrix multiplication must be defined. That means, the number of columns in the first matrix will be equal to number of rows in the second matrix. Zero matrix, also known as null matrix, is a matrix with all elements equal to 0. A symmetric matrix is a square matrix which is symmetric about its leading diagonal. So, if you consider this leading diagonal with elements 4 and 9, you see the matrix is symmetric around this diagonal. The other off diagonal elements are both -1. Similarly, this matrix is also symmetric. The diagonal matrix is a matrix where all the elements are 0 except the elements in the principal diagonal. Note that identity matrix is also a diagonal matrix, but there the elements in the principal diagonal are all unity. Here are some matrix operations properties. Matrix addition properties: A plus B equal to B plus A plus B plus C equal to A plus B plus C, A plus 0 equal to 0 plus A equal to A. Matrix multiplication follows these properties: A into B C is same as A B into C. Similarly, this, similarly this. If A is a square matrix of order n, and if p greater than 0, A to the power p is A times A times A up to p times. So, A to the power 3 is A times A times A. So, A to the power 0 is the identity matrix. So, if A is a square matrix of order n, A to the power 0 will be identity matrix of order n. So, here the matrix is a square matrix. The determinant of a square matrix. The determinant of a matrix A is denoted like this. It is also denoted as det of A. Determinants exist only for square matrices. For non-square matrices, determinants do not exist. So, determinant of a matrix n by n, which is shown here as follows, can be obtained by this. Here small aij represents the elements of the matrix A, capital Aij represents the cofactor of the elements in the matrix. So, the cofactor is defined as, say, cofactor Aij is defined as -1 to the power I plus j into the determinant of the matrix after deleting ith row and jth column. So, let us consider, I want to find out the cofactor of the element A21. So, what I will do is, I will delete the row and column containing elements A21. Then the part of the matrix that is remaining, you form a determinant and then the sign of that will be -1 to the power I plus j. Here I is second row, 2, j is first column, so 1. So, -1 to the power 3 into the determinant that exists after deleting second row and the first column. So, that is how the determinant can be obtained for any square matrix of order n by n. If you look at a 2 by 2 matrix, so the determinant of a 2 by 2 matrix is A11 into A12, A11 into A22 minus A12 into A21. So, basically you first multiply this and then minus multiply this 2. So, that is how you can obtain the determinant of a square matrix. Here are some properties of determinants. The determinant of matrix A and the determinant of transpose of A are same. We will see later what we mean by transpose of a matrix. You basically, by transpose of a matrix, you change the rows into columns and columns into rows. If a row or column of matrix A equal to 0, then the determinant of A equal to 0. If every value in a row or column is multiplied by, say, scalar k, then the determinant of A equal to the scalar k times the determinant of A. If two rows or columns are identical, the determinant of A equal to 0. If two rows or columns are linear combination of each other, determinant of A equal to 0. Determinant of A remains unchanged if each element of a row is multiplied by a constant and added to any other row. Determinant of the product AB is same as the product of determinant of A and determinant of B. Determinant of a diagonal matrix equal to product of the diagonal elements. Consider the M by matrix, consider the M by n matrix as shown. So, if I want to take the transpose of this matrix, what I will do is the rows of this matrix will be converted to the column of the transpose matrix. If the matrix is represented as A, the transpose of the matrix will represent as this, or like this, A prime or A to the power t for transpose of A. So, the matrix A has this as first row. In the transpose matrix, look at here, this becomes the first column. Similarly, you have this as the second row in matrix A. So, in the transpose matrix, this becomes the second column, so on and so forth. So, the rows of matrix A becomes columns in the transpose matrix. An n by n matrix A is said to be symmetric if A transpose equal to A. So, for a square matrix, if the transpose of the matrix is same as the original matrix, the matrix becomes symmetric, or we call this matrix as symmetric. Remember these properties: transpose of product A B is equal to B transpose into A transpose, A B inverse equal to B inverse into A inverse, A transpose to the power inverse equal to A inverse to the power transpose. Inverse of a matrix. Let A denote n by n matrix. Let us also consider another n by n matrix B, such that the product A B equal to the product B A equal to the identity matrix I. So, we have a matrix A which has dimension n by n. Let us consider another matrix B with the same dimension n by n, and if A B equal to B A equal to identity matrix I, then if such matrix B exists, we call matrix A is invertible and the matrix B is called as inverse of A, and we represent the inverse of A as A to the power minus 1. Let A and B be two matrices whose inverse exists, and let C equal to A B. Then the inverse of the matrix C exists and C inverse equal to B inverse into A inverse. Here are some properties of inverse of a matrix. The inverse A inverse is defined such that A into A inverse is equal to identity matrix I. Not every matrix has an inverse. If no inverse exists, then the matrix is called singular matrix. It is non-invertible. The determinant of that matrix will be equal to 0. If A is non-singular, then A inverse is also non-singular. If A and B are non-singular, then AB is also non-singular and AB inverse equal to B inverse into A inverse. A B C inverse equal to C inverse into B inverse into A inverse. Please note the reverse order. If A is non-singular, then its transpose is also non-singular. Also A transpose inverse equal to A inverse transpose. Rank of a matrix. The rank of a matrix is defined as the number of linearly independent rows. It can also be defined as number of linearly independent columns. So, the rank of a matrix is equal to number of linearly independent rows or number of linearly independent columns. If a matrix A of dimension m by n, where n is less than m, is of rank n, then A has maximum possible rank and is said to be of full rank. Rank of 0 matrix equal to 0. As long as A is not a 0 matrix, the rank of A will be greater than 0. In general, the maximum possible rank of m by n matrix is minimum of m and n. So, if you have m rows and n columns, the minimum between the two is usually the maximum possible rank of the matrix. There are certain operations which we call elementary row and elementary column operations. When you perform the elementary row or elementary column operations, you get an equivalent system. There are 3 elementary row operations or elementary column operations which you can perform on a matrix, and that will yield an equivalent matrix. They are interchanges, scaling and sum. First, 2 rows can be interchanged, 2 columns can also be interchanged. So, if 2 rows or 2 columns are interchanged, you get equivalent matrix, nothing changes. Multiplying a row by a non-zero constant, you get equivalent system. You also get equivalent system by multiplying a column by a non-zero constant. Third, the row can be replaced by the sum of that row and a non-zero multiple of any other row. You can also perform column operations. So, the column can be replaced by the sum of that column and a non-zero multiple of any other column. So, these 3 operations are known as elementary operations, and by performing elementary operations, you will get an equivalent matrix or equivalent system. Elementary row operations do not change the rank. One can use elementary row operation or elementary column operation to find the rank of a matrix as follows. When you do elementary row operations, minimum number of rows with at least one non-zero entry is the rank of that matrix. Similarly, when you perform elementary column operation, minimum number of columns with at least one non-zero entry is the rank of the matrix. Let us now talk about linear systems in matrix form. So, basically, how do I express a linear system of equations in matrix form? So, you have n equations in n variables, they are all linear equations and they are written as shown: a11 x1 plus a12 x2 up to a1 n x n equal to b1 and so on and so forth. So, this can be written by this coefficient matrix, which is an n by n matrix, this column vector which is x1 x2 up to xn and this right hand side vector, which is these vectors on the right hand side. So, using matrix notation, you can very neatly write it as A into x equal to B, where A is the coefficient matrix which is order n by n, you have n equations, n variables, x is a n column vector and B is this right hand side vector, again n vector. Now, this n linear equations in n variables can be compactly written in matrix notation as x equal to B. So, this equation allows us to solve for x also. Pre-multiply this equation by A. So, A inverse, pre-multiply by A inverse. So, A inverse A x equal to A inverse B. A inverse A is identity matrix. So, we can get x equal to A inverse B. So, you can solve for this linear system of equation as x equal to A inverse B. The linear system of equations x equal to B has a solution or said to be consistent if rank of A is equal to rank of augmented matrix A B. That means, you have this matrix as A and then put this column vector B here. So, another column in the matrix A comes from this vector B. So, that is known as augmented matrix. So, the linear system of equations x equal to B has a solution or said to be consistent if rank of A is equal to rank of the augmented matrix A B. A system is inconsistent when rank of matrix A is less than rank of augmented matrix A B. The system has a unique solution if rank of A is equal to rank of augmented matrix A B equal to n, where n is the order of the system. Next, we will talk about Gaussian elimination, which is useful for solving set of linear equations. By using elementary row operations, a matrix A is first transformed into an upper triangular matrix. Upper triangular matrix means all elements below diagonal will be equal to 0. Then you can easily perform back substitution to solve the upper triangular matrix. So, Gaussian elimination is an efficient way of solving set of linear equations. The first step is to perform elementary row matrix operations and convert the matrix A to an upper triangle matrix. So, we get an upper triangular matrix where all the elements below the diagonal are 0. Then perform back substitution to solve the upper triangular system. So, this is shown in this figure. So, you have A x equal to B as the system, which is converted as x equal to B again, but since I have done the elementary row operations to convert the matrix A into an upper triangular matrix, see that below this principal diagonal all elements are 0, and then it becomes easy for back substitution, because you get x n is equal to B n by A n n. Once you get this, you put this value in the preceding rows or preceding equations, you get the value for that variable and so on and so forth. Here is a simple example of Gaussian elimination. You have this matrix A, coefficient matrix and x1, x2, x3. So, 3 by 3 matrix coefficient matrix Ax equal to b, this is the b vector, this is the x vector and this is the matrix A. So, you perform Gaussian elimination to convert this A matrix into an upper triangular matrix. So, we have done it here. See, all the elements below the principal diagonal are 0. So, this remains unchanged, the first row. Look at the second row. 2, 1 element must be 0. So, this has to be converted to 0. So, what do? You perform elementary row operations. You divide row 1 by 25. So, this becomes 1, multiply that by 64. So, it becomes 64 and subtract the result from row 2. So, this becomes 0. So, that way you convert this element is also 0 by performing row operations. So, finally, you get this. So, from here you see x3 equal to 0.735 divided by 0.7. So, once you get x3, you put it in this equation, you will get x2, you put here in this equation, you will get x1. So, this way you can solve a system of linear equations by Gaussian elimination. Finally, let us briefly talk about eigenvalues, eigenvectors of a matrix. Let A be an n by n matrix, let x be a vector and lambda be a scalar such that Ax equal to lambda x. So, I have a vector A, I have a vector x and matrix A and a scalar lambda such that Ax equal to lambda x with vector x is not equal to 0. Then lambda is called an eigenvalue of matrix A and x is called an eigenvector of A. Look at here, A minus lambda I is identity matrix into x equal to 0. So, the determinant A minus lambda I equal to 0 is the condition for an eigenvalue. So, to find the eigenvalues, you have to solve A minus lambda I equal to 0. You have to look at this determinant, you have to solve this equation. So, A minus lambda I equal to 0 is basically this determinant equal to 0. So, this determinant is a polynomial of degree n in lambda. So, if you solve this, there are n possible eigenvalues lambda 1, lambda 2 up to lambda n. Why? Because the determinant A minus lambda I or this one will become a polynomial of degree n in lambda. So, a polynomial of degree n in lambda will have n roots. So, lambda 1, lambda 2 up to lambda n are the n possible eigenvalues of the matrix A with dimension n by n. So, with this I stop our discussion on review of linear algebra as well as the discussion on week 1.